Welcome to the part 3 of the lecture series on mechanical spring. So this is part 3. And let me change the color of the pen. I will change it to the green as usual. And in this lecture, we will talk about the design of helical compression spring under static load. And then we will go to design of helical compression spring under fatigue load. So this is the design of helical compression spring under. Now, few things that we have to take consideration of while designing the helical compression spring. One is about the spring index. This spring index has to be between 4 and 12. And if you remember that in first lecture, part 1, we said that we don't want basically a spring index to be less than 4. Why? Because it is difficult to manufacture. And we don't want it more than 12. Why? Because it has a tendency to buckle. So that's one condition. That's a recommended range. So remember, we need to use this in assessment, in doing design calculations, assessment of the design work. The second is a recommended range of active turns, means number of active coils. The number of active coils should be between 3 and 50. Then we will see that what is the maximum operating force that should be. You remember that a spring is like this, a compression spring. It may have many coils, and it is subjected to a compressive load, and when we compress it, it will come to the point that the distance between the coil will start to decrease, right? It will go further down. Means, let me draw it again. In other words, that it will just become like this. Now you look at it over here. What is happening here? All the coils are touching each other. All coils are touching. Each other. And this is we call the LS, shut length. And I need a force to apply to create this shut length. And that force is Fs, which is mentioned here. So we should not apply a load which will bring the spring to the shut length. In other words, that the maximum force must be less than 7/8 Fs, where Fs is the shut force. Now, what is the recommended value? The recommended value that we always define over here a parameter which is called the robust linearity or the fractional overrun to closure, and we set the value of this one to control basically that it should not reach to the shut length. And the way we will basically do, what the recommended value is, that the value of this parameter must be greater than 0.15 or equal to it. It cannot be less than this. So what we will do in our all calculations, we will basically start with a value of 0.15. The next one is the what we call the factor of safety at closure. So we need to have a factor of safety. That factor of safety is defined as the yield strength in shear divided by the shear stress in the spring. And this should be greater than or equal to 1.2. That's another condition. With these conditions, we can start what we call the spring design process. It is an open-ended process. There are many possible solution paths, and there is not one solution, there are more than one solution. And that we will have it in the design of helical compression springs. So let me recall it. The first one is that is regarding C, cannot be more than 12 and less than 4. The second is the number of active coils should be between 3 and 15. The robust linearity parameter should be greater than or equal to 0.15, and the factor of safety at shut should be greater than 1.2. With these, you can see over here these parameters I'm talking about. We calculate all the parameters which are given on this slide. This is also given as figure 10.3 in your book, page 521. Next, these are the parameters which you already know. You know D, you have calculated D, you have calculated spring index, you calculated outer diameter, you have calculated active coils, the shut length, the free length, the critical free length, the factor of safety at closure, and the figure of merit. So what I want basically now to do is to generate a table. So the table, the way I will generate it, it will look like this. I will have the table, and here I'm going to put the wire diameter, and then I will say, okay, now let me put D, C, OD, the active coils, and so on. So this will go like this and like this one. All the parameters up to the last one is FOM, figure of merit. And what I'm going to put over here is the diameter. So suppose I have started with 2.03 that we selected. The next one, I don't know, maybe let's say 2.2, let's say 2.4, 2.7, and here I will go, let's say 1.9 and 1.6, and I'm going to create. Now you can see the way the table is created. Once this table is created, means the entire design map is with me. This is the complete design map of HCS for given parameters. Now what I will do, I will start checking which one violates C. I will eliminate those. I'll say, okay, this one, suppose, doesn't basically, so if this one violates, this one violates, I don't know, well, means, well, just, it's a hypothetical case. OD, there is a limit, so maybe these two are not possible. Number of active coils, maybe this is not possible, right? The FOM, maybe these are not possible. Then I'll be left with very few choices which I have to make a decision, and I will select basically that one as my final design. We'll go through the exercise and you will learn more once we do the examples on the design of a spring. Next is the design of helical compression spring. Now we will talk about the fatigue load. In the fatigue, basically, we'll follow the same procedure to use the criteria as what we have seen in chapter 6. But what we need to do, we need to find out the fatigue, the strength, and particularly what we are interested in, the endurance strength. So the endurance strength, and if we consider the infinite life, means the n is greater than 10 raised to the power 6 cycles. Then one of the researcher, Zimmerli, has found that the size, the material, and tensile strength have no effect on the endurance limit of SE if the wire basically is less than 10 millimeter diameter. So what we are going to do is that we need to find out the endurance strength. How we will find the endurance strength of the material? So first what we need to know is the alternate endurance strength, which is this or this, and the mean, which is this. Alternate is this and mean is this. And you see over here the two words, peened, unpeened and peened. Unpeened means nothing is done, but when you do the peening, you increase the strength of the material. So what is peening? Peening is a procedure. It is used by manufacturer to increase the operating capabilities of a metals used in components. One of the method is called short peening. And what it does, it increases the material's strength. And you can see from here between these two that this one is greater than this one is greater than this because of the peening process. To just identify that, here is, it talks about the torsional modulus of rupture, and which is nothing but the 0.67 of S ultimate, and S ultimate you will get it from table 1004 in your book.